So far in the course, the discussion has been on a large number of topics, including transmission lines, impedance matching, that is an application of transmission lines, and several other aspects that are directly or indirectly based on transmission lines. We have also analyzed many of these networks. We have analyzed many of these configurations using transmission lines for various applications such as division of power, sending a wave from one point to another point, and in general ensuring that the power from a source essentially goes to a load in the broader sense. But if we were to look at RF applications as a whole, the crux of the applications of the domain of RF circuits and systems are essentially in the areas of communication. In this day and age, it is towards wireless communications, radio sets, and when I say radio, it's not always the definition that talks about the old radios for entertainment. Any wireless transmission and reception can be called as a radio, including the mobile phone in the hand. So therefore, if we were to look at such wireless transmission and reception, the first thing to note is that most of these transmitters and receivers compose of subsystems or blocks which are active in nature. Now, active means those devices or circuits which need an external biasing or power supply to do their function. On the other hand, in the course so far, we have looked at transmission lines and a number of applications using those, and those are essentially passive devices. Putting a long story short, look at them as a pair of wires and more. So over there, what happens is we need to concern ourselves only with the signal, the source, and the load. Additionally, no extra DC power is needed. So therefore, those are called as passive devices or circuits. However, as I was saying just a while back, that many of the components in the transmitter receiver, they are active in nature. So let us say we have something as simple as a modulator to send the signal to modulate the signal in the form of a new signal comprising of a carrier that sort of puts the information signal at a better position for communication. So if I have my information signal, I combine it with a carrier, and then this forms a new signal which is to be sent or transmitted. So therefore, what we have over here is an amplifier. And finally, we have an antenna. This is a transmitter. If we were to look at a receiver, we again have a receiving antenna which sort of receives the signal. We again have an amplifier at the receiving end which is expected to boost the strength of that signal. And finally, we have a demodulator. and from here we get the information signal back. So predominantly our aim now has been so far in the course to look at these places, the lines that are connecting two blocks. So essentially these are all transmission lines. Transmission lines, impedance matching, and so on. Now this is a very simplified version of what a transmitter and receiver look like. In reality there are many more blocks. So in those blocks you may often need power dividers, power combiners, hybrids, coupling structures, and more. But the point that I am trying to make over here in this particular discussion is that the blocks, these modulators, demodulators, amplifiers, and so on, they are essentially active devices or active circuits. So to take an example, to take some examples, we have amplifiers, which are the best possible example of RF circuits. So what essentially happens is that if you were to look at a transmitter and a receiver, the amplifiers, they may look the same, but actually they are doing two different functions. If you were to look at the transmitter, let us say I have a mobile phone in my hand. If we were to look at the transmitter of that mobile phone, the amplifier here has just one job. It does not have a very clear idea of where the nearest base station is. So what it essentially has to do is to take this final signal, this modulated signal, and provide the maximum possible gain over here. Provide the maximum possible gain so that the antenna can pump out the maximum possible power. This kind of an amplifier, where the concern is on the highest possible amount of power that can be transmitted, these kind of amplifiers are called as power amplifiers. Now, power amplifiers are not just used in RF applications or RF transmitters. You have also come across the use of power amplifiers in a more daily life, although whether it was realized at that point or not, that is questionable. For example, many of you may like to listen to music, and for that you may like to use your headphones, or if you are having a party you can use a speaker. So effectively what happens is that in those headphones or the speakers there exists a power amplifier, although those are called as audio power amplifiers, which essentially have to take the music signal and provide the maximum possible amount of output power that it can possibly provide. So that is another example of a power amplifier in audio. On the other hand, in the receiver, this also has to provide gain. Of course, both amplifiers have to provide gain, that is a given. But over here, the job is slightly different in the receiver. What is happening is that the signal that is received by a wireless receiver is generally very weak in magnitude. And also there is a lot of noise in the ambient. Because of that, the signal is not very clear. Whereas over here the signal is much more clear in the modulator output, and the received signal is not very clear. It is often buried in noise. For example, if you have to receive a wireless signal on your mobile phone, it can be as weak as -80 dBm, -90 dBm, or a -100 dBm. So you can think in terms of milliwatts, that is such a small fraction. So therefore, this amplifier has to be extra sensitive. It has to be able to amplify the signal and not the noise that is with it. So therefore, these amplifiers are called as low noise amplifiers. So power amplifiers in short are called as PAs, and low noise amplifiers are called as LNAs. So the best example of an RF amplifier is a PA and LNA. PA in the transmitter, LNA in the receiver. Next example of RF circuits. One of the best example is in the case of demodulator. If you recall what a super heterodyne receiver looks like, essentially it has to down convert a modulated signal into a lower frequency form so as to extract those circuits back, extract the signal back. So those are essentially called as mixers. So these are for up conversion or down conversion of frequencies. Anything else? We have oscillators also. Oscillators are essentially circuits which can generate RF signals. Generations of RF signals. Any other example? Ultimately, when the information signal is there, it is not in its purest form, so therefore it has to be detected using a detector. Power detectors, for example. So detectors are also active networks. So these are some of the examples of RF circuits which are active in nature, and therefore they need, at least the basic idea behind these need to be looked at. Now when we discuss about active circuits in general, for low frequency applications also in your basic circuits course, over there, for active devices, generally some kind of semiconductors are always used. So active circuits need to make use of active devices, and those are semiconductors, also called as solid state devices. So usually when we look at amplifiers, for instance, the best example that comes into mind is a transistor as a device. So obviously the transistors which we looked at in our basic circuit labs were for low frequency use, and therefore at high frequency they have multiple problems. But when we look at circuits from a very basic perspective, transistors is not the first topic that comes into mind. The first topic that comes into mind is diodes. So diodes, as you know, are essentially PN junctions, and in your basic circuits course you would probably remember that the diodes are used for a number of applications such as rectification, clipping, clamping, and even for switching. So one of the best example is what we call as a PN junction diode. So the symbol of a PN junction diode looks like this. This is the P side, this is the N side, this is what is the anode or the plus terminal, and this is the cathode or the minus terminal. Right? So as you know, when this diode becomes forward biased, that is, the voltage at the anode exceeds the voltage at the cathode by a substantial amount, which is also called as the built-in potential of the diode, then the diode starts conducting and the current flows from the anode to the cathode. Whereas, so we'll say like this. So current flows from P to N. Now, whereas in the reverse bias, that is when the voltage difference between the P and the N terminals is less than what is the built-in potential of the PN junction, there is ideally no current. The current essentially tends to zero. Now, let us suppose we have this PN diode which is fed with an RF source. So ideally what we expect, if we were to look at the load voltage, so let us say for low frequencies, the voltage across the load VL would look something like this, kind of like a half wave rectified signal, because in the negative half of the cycle this diode would be off. But let us now see if the frequency of the source is increased, what might happen? If the frequency of the source is increased, we need to look at this PN junction in a little bit more of depth. It is now not just sufficient to say that, okay, as long as the voltage is below the built-in potential, the diode should be off. It is not just sufficient to say that. Remember that the PN diode is made by fusing together or diffusing together two types of semiconductors. One is a p-doped semiconductor, the other is an n-doped semiconductor. That is, this side has trivalent doped atoms and this side has pentavalent doped atoms, so thereby creating a majority of holes on one side and a majority of electrons on the other side. What now needs to be looked at is how the PN junction behaves in the reverse bias. So if we were to look at a 3D view of the PN diode, it might look something like this. So let us say this is the P side, this is the N side, and here is that border where the two are fused. So what happens is, in the reverse bias, there exists something called as a depletion region. Not just in the reverse bias, even in a condition without any bias. So if you were to look at this junction as a transparent element, it would look something like this. So what effectively happens is, if I put a negative voltage over here and a positive voltage over here, this is reverse bias. Effectively, this depletion region starts becoming more and more dominant. That is like saying there are only fixed ions in this region and there are no free charge carriers. So this is the depletion region. Now suppose this depletion region has some separation between these 2 points. Let us say we call it the width of the depletion region. Let's call this as XD. So this XD essentially indicates the width of the depletion region. Now, as the reverse bias is made stronger and stronger, what happens is the holes on the P side are attracted more towards the supply, and the electrons on the N side is also attracted more towards the positive supply. Therefore, what happens is that the depletion region starts getting thicker and thicker. So therefore, as the reverse bias is increased, the depletion width essentially increases. Now, what is important to note is it is not just the depletion width which is increasing. Electrically, it has another effect. That is, now this plate and this plate, these two plates are essentially like the border between the charge carriers and the place where there is no charge carrier. So what is essentially happening is that over here at these plates there are these free holes which are getting attracted towards the negative. And on this plate there are these electrons which are also getting attracted towards the positive. What is effectively happening is that there are two plates of opposite charges separated by a distance xd. So therefore, this essentially forms a phenomena similar to a capacitor, and this capacitor is called as a junction capacitance. PN junction capacitance. So therefore, what effectively happens is that this junction capacitance, also called as Cj, that will be a function of the size of this depletion region. So let us say that this is some L and this is some W. So the plate area is L times W. So the junction capacitance will be the epsilon of the silicon or whatever is the semiconductor that's being used times the area divided by the plate separation, which is XD, and over here area is L times W. Now, obviously we can see that as the reverse bias is increased, XD increases, so therefore Cj reduces. But if you go with the usual PN junction diodes that you have used in your basic circuits lab, so usually for most diodes this length and width are very large. So in the reverse bias, what is happening is that there is a capacitor. There is a capacitor of a pretty large value because of the large area. So now in the reverse bias, if I have an RF signal, if I have this, essentially what is happening is that ideal diode looks like this, an open switch, but a practical diode would look like a capacitor of value Cj. Therefore, effectively what is happening is that for a high frequency signal, the diode acts like a capacitor. and this will have a reactance Xj that is equal to 1 by 2 pi F times Cj. So if F is increasing and Cj is very high, this Xj will become very, very small, and therefore it will almost behave like as if there is no open circuit. It is almost a short circuit because the reactance is very, 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 very low, and that is disastrous. This is disastrous. So therefore, the standard PN junction diode is almost useless in case of the RF signal or RF frequencies or at very high frequencies. So what we can see from here is that in the reverse bias case, this impedance of the diode in the off condition must be as high as possible. Therefore, since we want a diode which can operate at as high frequency as possible, this Cj must reduce. So therefore, we need very, very low Cj. We need very low Cj. Now what you can see over here, Cj depends on the permittivity of the silicon material, the area, and Xd. So one thing that we can immediately do is we can reduce the area. So diodes with low A. But what happens is that is not just enough. What we can do is we can also increase Xd as much as possible. Now one way to increase the Xd, as we saw, is to make the depletion width thicker and thicker. So effectively the capacitance will reduce. But that process, what happens is, for the capacitance to become sufficiently low, you need to give a pretty high reverse bias. To make Xd high, you need to give a pretty high reverse bias. Now that is again another problem. What if we don't have that kind of a voltage source available with us? Well, in that case, a very small modification can be done to the PN junction, where without having any reverse bias or without having any strong reverse bias, we can still obtain a very, very low capacitance. And thereby, I introduce the very first type of specialized RF diode, and that is called as a pin diode. So the pin diode essentially looks like this. It has a P-type semiconductor, it has an N-type semiconductor, but in the middle there is also something called as I, and this I stands for intrinsic. It has an intrinsic semiconductor layer. Now, as you know, intrinsic semiconductors by themselves at equilibrium at room temperature are insulators. To make semiconductors have conductive properties, we go for doping. So these P and N are doped regions, but this I is an undoped region. So thereby immediately what is happening is that the depletion region essentially becomes like this. This is the entire depletion region. So therefore this Xd is now much higher than what it was earlier. So immediately I can say that the junction capacitance will be very, 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 very low. Very, 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 very low. So now if we were to draw the symbol for this, the symbol looks quite the same as a normal diode. Usually what is done is that this part is blackened. This is the symbol. This is one way in which we can make the junction capacitance a lot smaller. Now, even if we have made it smaller, so what? Even if we have made it smaller, so what? There exists another problem. There exists another problem. Let us see what that is. Again, let us take this PN junction or this pin diode and connect it to an RF source. And over here, we have some load. Now, what happens essentially is that when the diode becomes forward biased, it starts working like a normal PN junction, as you are familiar with. The only difference is now in this large depletion region. We are now increasing the depletion width to get a smaller junction capacitance. But what we are doing essentially is that we are inviting another kind of trouble. That is, the depletion region by itself has its own built-in potential. Okay, and the electric field that is associated with it does not allow the charges, the free charges from the P side to the N side or the N side to the P side to travel that fast. Think of it this way. Think of it this way. There's a bucket of water, or there's a bucket which you are filling with water. And then you are making a very, very tiny hole at the bottom surface of the bucket. So what's going to happen is that the bucket will now become the depletion region. Now, because of that small hole, the charges will jump into the depletion region, but they will not be able to exit as fast. So although the tap will be on at full flow, a lot of water will start entering the bucket. But because of the small hole, the water leaving the bucket will be very, very small. And that is what this large depletion region does. So what you will see essentially is that there will be entry and exit, but at any given point of time, there will be a lot of free charges that will be trapped inside the depletion layer. Or we don't use the word trapped, we call it a stored charge. So the free charges get stored inside the depletion region at any given time, which are trying to move. Let us say the holes are trying to move from P to the N side, the electrons are trying to move from the N to the P side. So at any point of time, there are a lot of these stored charges in this region. So what effectively happens? What effectively happens is that because of the stored charge in the depletion region, the larger depletion region, the diode takes time to turn off. So suddenly if I change the forward bias into the reverse bias, so in the on condition, so if this is VL, in the on condition, the diode will conduct, definitely. Although the depletion region is there, it will pass charges. In the on condition, the question of the speed of charges does not matter, or how many charges are coming. The current may change, but what will essentially happen is that the diode will behave pretty much like a closed switch. And therefore, what will happen is that if the input is like this, in the positive half cycle, the output voltage will try to follow the input. Now, at this point, when the bias suddenly goes from positive to negative, the diode does not switch off immediately. The stored charges, because of their inertia, they are still trying to cross. Now, when we are changing the reverse bias, these charges also need to go somewhere. the holes on the P side start getting attracted over here and the holes on the N side start getting attracted over here. But what about the charges that attract? So these will also try to follow what the P and N sides are doing. The point now is that these charges will constitute a current. So therefore what we expect that in the reverse bias the voltage should go to 0. That will not happen. A current will start flowing in the opposite direction, which will try to follow what the input is. So therefore for some time it may look as if the charge, or it may look as if the diode is still on, which it is. Now until the time the charges have left the depletion region and have recombined with the other carriers, the minority carriers, there will be a brief amount of time when the diode will still conduct, and after it starts conducting, at a point it will suddenly again drop to 0, and then it will behave like a normal closed diode. So this time when the diode is still on, this is called as a reverse recovery time. This is called as reverse recovery time. Here it indicates the time the carriers, the trapped carriers, take to recombine with each other or somewhere over around. So in case some of the charges go over here or here, they manage to escape, very good. Otherwise they will recombine over here itself. You may have seen the effect of reverse recovery time on your desktop screens or the LED screens on your TV. What happens is that on the desktop of a computer or the TV, there exists a power LED. So if you notice, when you switch off the main supply, the LED still continues to glow for a little bit of time, because the carriers are plenty in number, they have not yet died out, and that is what is called as reverse recovery time. Okay, so essentially this reverse recovery time is now creating a problem for us. This diode then cannot possibly be used as a good switch, because we have reduced the capacitance, which is very good, but then what will now happen is that the RF switch or the RF signal will not be able to make this diode act as a good switch. Does it mean that this diode is useless? No, it's not useless. There is definitely a lot of use for this. I'll tell you what that uses. This diode can be used as a switch if it is controlled by an external bias element. It can be used to transmit the RF signal completely as long as it is biased by an external control voltage. Used as a switch with external DC control input. That is like saying you have something like this. These are the two terminals of the switch, let us say input and output, and this is called as the control. So one way to give this control is to have a DC voltage which controls the bias of the diode. So let us say V control is more than 0, that means diode is forward biased, so therefore the diode is on. And the VC is less than 0. Let us say, so this is reverse biased, the diode, so therefore it is off. Now because of the DC nature, the sharp switching, the reverse recovery will not play a very major role, and effectively what we want is that when the diode is forward biased, it should be able to transmit a whole RF signal, and when the diode is reverse biased, it should not be able to transmit anything or transfer anything. So what we are essentially doing, we are not using the RF signal itself as a switching element, but rather we can use this pin diode as a switch with an additional control element to transfer the RF signal from one end to another end. So let us say I have something like this. I have this pin diode, right? Now let us say I have an RF input over here, and then I have a load over here. Therefore, what I want is that when this diode is forward biased, this should act like a closed switch, and whatever is this signal will reach here. And when the diode is reverse biased, then this should act like a closed switch, and whatever is this voltage, that should not come here. So therefore, I must provide a means through which I can give this VC as a DC voltage, as a control element somewhere to the diode. Now what is happening, what I can do, I can essentially think of a connection over here. So if VC is positive, this one will try to become forward biased. But at the same time, what I should do is that I should also provide a path to ground for this conductor or this terminal, for the N terminal. Now let us say VC is positive, the diode is forward biased. So at this time, this signal must come over here. Now what will essentially happen is that when this signal tries to come over here, we are breaking the circuit theorem that at the same point we are having two voltages. One is an AC voltage, one is a DC voltage, which should not happen, and therefore it will create an anomaly. You are trying to have two potentials at the same point, which is not possible. So therefore, what we can do is we can take a leaf out of our biasing circuits which we have learned for our amplifiers, and let us say that we have to isolate this AC source from this DC source. So no amount of the DC source can come over here. So therefore what I can do, I can put a series capacitor over here. Let's call this as CC1, that means coupling capacitor. Or this is also a DC blocker. This is also called as a DC blocking capacitor. Now, what is needed to be seen is that if this capacitor is there, definitely no part of the DC will come here. And this capacitor can be chosen as a pretty large value so that this signal can come over here. But now again we have a problem. We again have the AC signal over here and a DC point over here, which will again cause the anomaly. So therefore, these 2 points need to be isolated in such a way that now this DC can come here, but the AC cannot reach over here. So what we can do, we can use an inductor over here. Let's call this as L bias. Let's call this L bias 1. Right? So effectively at this point what will happen? The DC will come as it is, because at zero frequency the inductor will act like a short circuit. But the AC signal cannot come over here because the inductor will give a high reactance or high opposition to the RF signal at high frequency. So this is the way we can have at this point VC plus, let's call this as VRF. You can effectively superimpose these two at this point. Now, the other question is that we have solved how to bias the P side. Now what about the N side? Definitely we need a path to ground. So what we can do, we can essentially connect it over here. That will solve the problem. But then what will happen? The VL, the load voltage, will now contain the control voltage as well as the RF voltage. Whereas we want only this voltage to come over here. So therefore, we can again put a DC blocking capacitor. We will call this as CC2. Thereby what will happen? this will be nearly about VRF. And this one we can bias it pretty much in the similar way. Why? Because we cannot use this capacitor because it does not then have a DC path. The capacitor will act like an open circuited DC, and we can connect an inductor over here. Let's call this L bias 2. So in the DC path will look like this. I'm drawing it with a bold arrow. Let's call this as IDC. And the IAC, I'm going to draw it using dash lines. I'll call it as IRF. This is a simple example of what we call as a control switch or a single pole single throw RF switch. Now there are a few things to be kept in mind. This RF signal has to be small in magnitude because the RF signal by itself cannot disturb the bias conditions. So therefore the magnitude of the RF signal must be less than the magnitude of VC. It should not be able to disturb the bias condition. So when this VC makes the diode on, this entire RF wave for both circles, for both cycles, the positive cycle as well as negative cycle, should be able to come over here. And when the VC is off, that is when the diode is in reverse bias, no part of this should be able to come over here. So therefore what we have done, by keeping the RF voltage small, we are not letting the reverse recovery time of this diode play a role in the reverse bias. Secondly, this spin diode, we have designed it in such a way that its depletion region is much larger. So therefore it has a smaller capacitance, which makes it act like a better reverse biased offstate diode. Therefore, this can be used as a good switch. But do not forget, the switch has to be powered or operated through an additional control voltage. It is the question of whether the entire RF signal is sent from one point to another point. Other thing to keep in mind, no matter how I have drawn the circuit, the assumption is that the sizes of the components and the wires are all less than lambda. They are not just less, they are much less than lambda. Because if they are not, then the transmission line elements will come into picture. So in reality, what will happen is that you will have to essentially place the elements very close to each other, and thereby you have to make a very compact circuit which is much smaller as compared to the wavelength of the signal that is being generated by the RF source. So this is a very simple way through which we can essentially make a controlled switch using a pin diode. Now this is also called as a series connected switch. Because the diode is in a series connection, you can make a very simple modification to this circuit and have the diode in the shunt configuration also. The other thing is that the switch can conduct only from left to right, not right to left. And there is a single control voltage. So therefore, this kind of switch is also called as an SPST switch, single pole, single throw switch. This is the way you can use a pin diode to make an RF switch. And it is one of the simplest examples of how to use an active solid state RF device, in this case the pin diode. So in this lecture, we looked at the very basic foundations of active devices in RF circuits, and we discussed thereafter the drawbacks of the PN junction, the conventional PN junction which we use for low frequencies, but they are bad at high frequencies. And we looked at one diode with a very low junction capacitance which is suitable for RF frequencies, and that is a pin diode which can also be used as a switch, a control switch. We shall continue from this point onwards in the next lecture.